So today I'm going to be co-presenting with Serge, the integration of the mixed-signal IP. It's a MPD5 CSI2 interface with inside the Renesas chip. So I'll start actually by giving an overview on Mixel, and we'll also give an introduction to the MIPI. For those of you who are not familiar with the MIPI, we'll give an overview about the D5 and the CSI2 interface. CSI is a camera serial interface. And then Serge will be adding color from functional safety perspective, integration. And we'll also be talking about the mixed signal IP integration, not only from functional safety perspective, but also from the reliability and quality point of view. Okay, so Mixel, we're actually a leading provider for mixed signal IP with focus on PHY. We've been in business for the last 20 years. We're an industry leader for the MIPI interface. We've been a contributing member at the MIPI Alliance since 2006. We're actually the first IP vendor to demonstrate silicon-proven D-PHY IP, and then N-PHY, and then C-PHY IP. And our solution for MIPI is we provide an integrated solution where we provide the physical layer, the controller, and also the validation platform. So although we provide a standard interface IP, but we're still very customer-centric focused. So we customize our IPs quite a bit to help differentiate our customers' product. For those of you who are not familiar with the MIPI Alliance, it's a global organization established 2003 with more than 300 members. Sorry. With more than 300 member companies. I think most of your companies are members in the MIPI Alliance. The focus of the MIPI Alliance was mobile, but with the development of mobile influenced markets, now the MIPI specifications exist in more markets other than the mobile. So it exists in IoT, it exists in virtual reality markets, and also, of course, in automotive. So this is kind of a picture of all the different specifications developed at the MIPI. So it's kind of, the MIPI specifications are classified into 3 layers. So the first layer is the physical layer, many specifications developed there. Also, there's the protocol layer and the application. So the main thing which is common between all those specifications, they share the 4 main pillars for any MIPI specification, which is the high performance, the low power, low EMI, and low pin count. So this is a quick introduction to the MIPI D5. So it's actually the de facto standard for camera and display, connecting megapixel cameras and displays to your application processor. So in your cell phone, you have a camera sensor, you have a display, and it's connected to the application processor using the D5 interface, or lately also could be C5. The D5 is very flexible. It's actually optimized for both high performance, high speed, and low power. The D5 is actually uses a forwarded clock DDR architecture. So you have a clock lane and a data lane, multiple data lanes in your D5 lane. Sending the clock with the data allows the D5 to have high immunity and high jitter tolerance compared to other standards. And the D5 is steadily evolving generation after generation in speed. Actually, the first generation for D5 we started with less than 1 gigabit per second per lane, while the latest standard coming out in early next year, it will target higher than 10 gig per lane in the D-PHY. And of course, the D-PHY maintains backward compatibility to all the previous generations. So this is an overview on the Mixel D-PHY IP we provide. So we have the D-PHY IP in many multiple configurations. We have the universal configuration, which has both the transmitter and the receiver inside the same IP. So this is kind of, it supports all the different use cases, but it's not optimized for area or for leakage power. We also have use case optimized configurations such as the CSI transmitter, CSI receiver, and DSI transmitter and receiver. On top of these configurations, we also have our proprietary configurations, which we call TX Plus and RX Plus. This is for both the CSI and the DSI. And these are optimized for automotive applications. They help us achieve a higher ISO grade, and also optimized for production testing. So they enable full loop-back testing, which can also be used for periodic checking of faults or other initialization or periodically. Our IP actually believe it has the widest coverage in the market. So it's silicon proven in 9 different nodes from 180 nanometer to the FinFET technologies and in 8 different foundries. So this is some of our MIPI PHY customers. There are other customers which are not disclosed here. So I'll be giving you some quick overview on what is happening in the MIPI alliance with respect to automotive. So as we mentioned, the MIPI specifications are diffusing into automotive applications. And in some of the latest use cases, this will require the highest level of functional safety support. And the MIPI Alliance is addressing these challenges by revising some of the existing specifications, in particular the CSI2 and the DSI2 specifications, in addition to developing a new physical layer just for automotive. But why is the MIPI D-PHY and C-PHY and the CSI2 interface very popular in automotive? There are 5 differentiating factors. So of course it's a standard interface compared to some custom solutions. So it makes it very easy to interface transmitter, like a wide variety of transmitters and receivers. High bandwidth. For both D-PHY and C-PHY, you can achieve very high bandwidth. And low pin count. So there's also a lot of flexibility associated there. So for the D-PHY or C-PHY, you can have 1 lane, 2 lane, 3 lane, or 4 lane configurations, which provides very good flexibility. At the same time, there's also support for, there's virtual channel support where you can actually aggregate multiple sensors or multiple CSI channels into a single lane, of course, if your bandwidth requirements allows that. So this kind of provides a lot of flexibility for the system integrator. From functional safety perspective, the PHY and the CSI interface, they provide multiple error correction and detection mechanisms. So the physical layer provides sync codes, which are sent from the transmitter to the receiver. At the same time, the controller provides ECC and a 16-bit CRC. In addition to that, there's a chance or there's support that safety-related metadata are sent along with the Mixel. So today's use case for the CSI and the D-PHY, they are integrated into the camera sensors in the automotive application. And so this is the transmitter. On the other side of the link, the ECU, in the receiver, you have a receiver, CSI, and D-PHY or C-PHY. Most of the existing applications or use cases today for the automotive were like the sensors were used as the surround sensors, so mainly for rear view, for surround view, for collision mitigation and avoidance systems. But as we see through our customers, there are more use cases being developed to support LiDAR and radar application, which means that for the new generations, you need to support up to ISO D, or you need support up to ISO D with respect to functional safety. So this is like some of the points, or these are the main points getting considered the MIPI Alliance with respect to functional safety. So the first point is being targeted is the information redundancy. So the CRC has to provide a Hamming distance of 3 or more, which translates to a 16-bit CRC or 32-bit CRC, depending on the amount of data being transferred. So this is also a function of your data rate and bandwidth. The CRC has to be calculated on all the data packets, the header, the trailer, and the payload data. So this is being translated into a requirement in the revised specification for the CSI and DSI as a 32-bit CRC auxiliary filter. The second point being considered is the frame counter, and there's going to be a message counter which will be incremented and sent with the CRC protected data packets. Of course, this is monitored at the receiver side if any data packets are sent twice or are missing. So this in the MIPI specification is being specified as a message counter in the auxiliary header. The third item is the timeout monitoring, and this is the assumption is that this is currently handled at the system level, and it is not part of the CSI or DSI specification. So all of this is kind of protecting the data, like this is from the PHY and the controller to the PHY and controller. So it's protecting the PHY, the controller, and the transmission line. But you still need to add some support or provide support to the TX component. So TX component might be sending some additional control data besides the pixel data. So so based on that, protocols actually will be supporting on the component level that a second CRC and a second message counter is sent by the TX component in the CSI data packet and of course decoded at the receiver side. So in addition to revising the CSI2 and DSI2 specifications, there's also a dedicated PHY developed for automotive, that's called the A-PHY, if any of you have heard of. So it's the advantage of the A-PHY, of course, it's going to be a standard interface versus the proprietary existing LVDS solutions. It is developed to support ISO D from the first specification. The first specification is coming out early next year, and the plan for the bandwidth support is to support between all the way between 2 gigabit per second to 16 gigabit per second. I believe the future revisions will even provide higher bandwidth support, higher than 16 gigabit. It supports up to 15 meter automotive environment. It will enable the use and reuse of billions of instances of MIPI protocols like the CSI2. So very quickly, the picture on top here is kind of the existing solution where you have an image sensor with sending data through a MIPI C5D5, and Then you have the custom service chip, which takes this interface and sends it through a coaxial cable channel to the other service chip on the other side of the link, which converts it again to MIPI CSI data, and it goes to your application processor. If I in short term should just replace this service chip, of course with the advantage of higher bandwidth and being a standard interface, and long term, the plan for the IFI is to get integrated into the image sensor and the ECU, which will eliminate this intermediate chip and optimize your link from cost perspective, from latency, and of course from functional safety perspective. So I'll talk very briefly on our mixed-signal IP, which is an IP developed as a safety element out of context. Of course, the very common issue is that the IP vendor doesn't have a thorough knowledge of the system, so we don't know the hazards, the safety goals, and the architecture. So we have to have some assumptions on the safety functions. They need to be general enough to support a wide variety of our customer expectations. At the same time, they need to be applicable to the customers, and we align actually these assumptions on the kickoff meeting with the customers. I should be co-presenting with Serge, so I think I'm kind of running late on my slide, so kind of maybe skip very fast through the. Okay. So assumptions of use, as everyone kind of mentioned, it's extremely important. This is some of our assumptions of use. We developed the DFMEA, and we focused on the high severity, low detection, and high severity, high occurrence risk matrices. We didn't put our focus on the RPN. And we, actually this is, we also worked on the FMEDA. I'm kind of running fast here, so I'm not going to get into a lot of these details now. And then the safety manual, this is kind of what we put in the safety manual, assumptions of use, the safety analysis, the FMEDA, FMEDA, and the DFA. And the last slide I have here is regarding reliability. So as a mixed-signal IP provider, we also have to worry about the reliability concerns, not only on the, so actually there's much more we should do as a mixed-signal IP provider from reliability concerns such as aging simulations, higher CPK, higher temperature simulation. So yeah, I'll just stop here. I'll give I'll give Serge the stage, and so he can share with us his insights.
Thank you so much. Thank you. Okay, thank you so much. From Renesas, IDT Renesas, it is going to be integrated into Renesas, and let me say, we are lucky to collaborate with Mixel for integrating the IP into this complex leader system, where we use, as we say, the light emitted by a laser diode, hitting an object, a target, and recognizing and operating the received light pulses with the support of mirror lens for generating a 3D imaging out of the world. The safety concept of this system that has been already developed in the first generation. Now we are going to develop the second generation with a much faster interface with higher bandwidth. And the safety concept is quite complex. It includes also let me say, the check monitoring of external elements. In other words, for this laser diode, we have integrated as a part of the functional safety concept an external photodiode dedicated to check that the laser diode is really in the factory, constantly generating the laser pulses. And at the same time, we have also an external LED that on regular, let me say, timing generates a a kind of test lighting to the array of the photodiodes for checking each of the 32 channels, the input channels. Okay, so the point is what we should be concerned about. This is not just, this is surrounding information, but the scope of this presentation is to show how much, we say, care we have put on considering the amount of failures at this level of the interface. Okay, so what's about this VP5? We have already said that we have several setting mechanisms embedded, like the timeout, like the embedded 16-bit CCITT CRC. And I think the question is why 32-bit additional CRC? What is good for? What problem is going to solve? Okay, let's analyze a little bit the characteristics of this interface, how it is used, how it is supposed to be used. We have to start with modelizing sorry for these the deep technical details, but I come from technical analysis. I cannot stay just with qualitative analysis. We need to understand what is the issue in terms of fit at the end. So if we consider the channel, and if you assume that the channels as, let me say, with equal probability to have an error, and we consider a Gaussian channel with noise generation on the channel, what we can say is that depending on the packet size that we configure for this interface, we may have a certain probability of error that is expressed by this formula. Very simple. What is inside here, 1 minus bit error rate, is the probability of right bit, that the bit is correct. Powered by n, this means that the sequence of n bits altogether is correct. 1 minus this term, okay, this is a probability, a complementary probability that we have a wrong packet, or an error, one or more errors in the packet. Okay, so according to the assumptions of use of this device, we may have several bandwidth for 2D applications, 3D flash, or 3D mirrors. And these are, let me say, how the reader is used for generating the picture. So, if we look at the probability of having an error in the packet, we see that this strongly depends on the packet size. It depends on the bit error rate. And basically, this just says that for certain very noisy environment and for high data packets, so the probability to have errors inside the packet is quite high. This means that we have a reduced bandwidth. Effective bandwidth is reduced by this factor. Is this a concern of functional safety? Not really. It's just a concern for the availability of the channel. What is the concern of functional safety is what's about the error. So we're interested at the errors. Like the physician, the scientist exploring the universe, are interested to understand where is the matter. Here as a functional safety managers, we're interested to see the well-known matter that is expressed by this, and more important is the dark matter. The dark matter are those failures which are undetected. Because we know that these failures, most of these failures, almost all these failures, are detected by the CLC or the ECC. But there is a small quota, a small portion of the failures which are still surviving, are still not detected by the CLC. So this is our concern. What is the probability of undetected failures? this is our concern. This is our dark matter, the probability of undetected failures. Because we know the CC ITT 16-bit CRC is well studied. We know almost everything about the diagnostic coverage of these CRC. What's about the complementary parts? Here the picture. This picture should be read carefully because the scale is reversed. So this means that this is the worst case that corresponds to the highest probability of undetected error per failure. And we have such bad results or bad figures when we have we know already, longest packets and high bit error rate. But this is still a probability. We have to translate this into fit, because at the end it refers to the fit. Which fit? Those ones affecting directly PMHF. This is what we refer to. On top of that, we were discussing so far just about the transfer failures. Bit error rates are just those failures occurring in this part of the communication. Nonetheless, I want to emphasize one point, that if we look at the physical implementation of the CRC 16 and CRC 32, we have a limited diagnostic coverage of the CRC, also for those permanent and transient failures occurring at one portion of the IP, the ones that basically include the file. But when using generating a share of the data, protecting the data with a 32-bit CRC that is appended at the input of the IP, with such measure we have covered the complete IP, including the channel, and including also the transmitter sides with high diagnostic coverage. Unfortunately, so, and this is what we are going to cover in terms of permanent and transient failures. Of course, this is true only if we can perform such check within the failure handling time interval. At least once every time interval is sufficient, while the CRC 16 is included in every data packet. So, I think, so this is the picture also. This is the situation we have when considering just the 16-bit CRC in terms of the translation of such probability of undetected failures into PMHF, and according to the different use cases, assumed use cases. I've generated the threshold of 1/5 here, just for showing the differences. And this is what we have when using 30-bit CRC. Summary, because I think the time is long. I want to leave just some minutes for questions, if any. So, 32-bit CRC seems to be quite expensive in terms of computation time and so on. But we have now processors, including hardware accelerators, including CRC checkers embedded in hardware. So this is no longer, this is now affordable without using software resources. I would like to leave some time for questions, if any.
Okay, so first we thank the two speakers. And so I think we have one question. Otherwise, we ask if you heard all IQPC number and table in one exam. No. Any question? Chuck, yes.
Oh my God, very challenging. It will be very challenging question.
No, I have a question to Ahmed. In your slide, slide 14, I think you said that you developed the file to support SEooC. So what does it mean exactly?
We're talking about the MIPI.
Yes, the MIPI file.
Yeah. It should be
This is,
this way.
I mean, this is the way that. Okay, so I mean, this is, they are considering, so for example, I gave some examples on the PCSI2 and VSI2 revised standards to allow functional safety to its highest level of support up to ISO. So it's not mandating something on the system, it's just allowing, if you need such support, you will have the tools to achieve that. And I think the numbers Serge have presented with the CRC 32 are kind of aligned with that example or that statement.
If I'm allowed to support in the project that we are considering, this is going to be integrated into the item as SED of D. This is why it says it can support up to SED application, SED requirements. Of course, always into decomposed items, because it does not work alone, but it's always supposed to work together with other sensing channels. There's the radar, there's the infrared, or whatever.
In fact, my point was most of the safety mechanism is implemented at the protocol layer, the layer 2 controller. So for the PHY, I would expect that it would be QM, like a CAN transceiver or link transceiver, and then the safety mechanism will be implemented at the protocol level or layer 2 level.
This is one of the possible SED decomposition, of course. Yes.
So yeah, very quick.
You showed that basically the probability of an undetected failure, even with the CRC16, is relatively small. And still you showed how that becomes a reasonable fit rate. Is that an assumption that basically any detected fault you kind of ignore it, or you are always going to re-read and you are basically going on forever, waiting for that unfortunate day, 10 years down the road, where there is an undetected error? Is that the underlying assumption?
The underlying assumption about the probability of detected failures are related to the bit error rate as generated during the communication channel or as generated by bit flips within the FP, because also those ones are sources of failures that must be detected. And in this project, just to underline, the transient failures are 98% of the overall failures for the amount of. And even considering that permanent failures are calculated on the basis of Siemens SL29K. So it's a really a matter of concern, the transient failures.
Okay, I think we are at the end of the time. So again, many thanks to you.